Have you ever wondered how engineers and physicists efficiently calculate the often complex magnetic fields generated by electric currents? Understanding magnetic phenomena is crucial in electrical engineering, but direct calculation can be incredibly challenging without the right tools. Thankfully, there is a powerful conceptual aid that simplifies these calculations dramatically in specific situations. An Amperian loop path is most effective when the current distribution generating the magnetic field possesses a high degree of symmetry. This symmetry allows for a significant simplification of Ampere's circuital law, transforming a complex line integral into a much more straightforward algebraic equation. Without this symmetry, the integral becomes prohibitively difficult to solve by hand or even analytically. The underlying reason for this effectiveness lies in the very nature of Ampere's law. It states that the line integral of the magnetic field B around a closed loop is directly proportional to the total current passing through the surface enclosed by that loop. For the integral to simplify, we need the magnetic field B to behave predictably along our chosen Amperian path. This typically occurs under for specific conditions. First, the magnetic field's magnitude must be constant and non-zero everywhere along the loop, allowing it to be factored out of the integral. Second, the magnetic field must be tangential to the loop path at every point, making the dot product in the integral straightforward. Third, the magnetic field could be perpendicular to the loop path, making the dot product zero, and thus the integral zero for that segment. Lastly, the magnetic field might be zero along the entire path, trivially simplifying the integral. High-symmetry current configurations naturally create magnetic fields that meet one or more of these conditions, making the line integral easy to evaluate. So, what kind of current distributions exhibit this crucial symmetry? Excellent examples include the magnetic field around an infinitely long straight current-carrying wire, where the field lines from concentric circles. Another is the field inside a very long solenoid, where the field is uniform and parallel to the axis. Similarly, the field within a toroid, or a donut-shaped coil, and the field produced by an infinite sheet of current also lend themselves perfectly to Amperian loop analysis. In each of these cases, you can cleverly choose a closed path, the Amperian loop, such that the magnetic field either has a constant magnitude and is tangential to the path, or is perpendicular to parts of the path, or is zero in certain regions. This strategic selection of an Amperian contour is remarkably analogous to choosing a Gaussian surface in electrostatics when applying Gauss's law. Just as a carefully chosen Gaussian surface can turn a complex electric field flux integral into a simple algebraic problem for highly symmetric charge distributions, an Amperian loop does the same for magnetic fields. It is a powerful conceptual shortcut, allowing you to bypass intricate vector calculus in specific, yet common, engineering scenarios. This understanding helps build a deeper intuition for how currents generate magnetic fields. Ultimately, by recognizing and leveraging symmetry, an Amperian loop path becomes an indispensable tool for quickly and accurately determining magnetic fields. It transforms challenging integral calculations into elegant algebraic solutions, providing a clear path to understanding the fundamental principles of electromagnetism in practical contexts. Mastering this technique not only simplifies problem solving but also strengthens your conceptual grasp of magnetic field theory, which is vital for any electrical engineer.